Hello, good morning, everyone. Welcome. It's a pleasure to present remotely. I would have really enjoyed to be in Copenhagen, but you're in very competent hands with Konstantin, I'm sure about this. Marc Rußwurm, assistant professor in machine learning for remote sensing at Wageningen University. I'm going to present to you some work on deep location encoders, and in particular to give an overview talk over how to encode geospatial data in neural networks, and maybe give a different perspective on how to use neural networks to learn geospatial data rather than to make a classification or a prediction. So let's get started. I will be talking about 3 points. So in the first part, I will cover basics and foundations and talk about how geospatial data can be stored in general as raster vector data, and how we can use neural networks to store geospatial data. In the second part, I will talk about how these neural networks are implemented and talk about a second line of research that has involved in that direction as well, and that structures the way those are implemented in the form of a positional embedding and a neural network to store the underlying data. And then both the research line kind of leads up to the recent work that we presented at ICLEAR this year. So I hope to give you a good overview on these 3 topics. So let's get started on the first one. So our world is inherently geospatial. Any data we collect on this planet has some location information in form of coordinates attached to it. And those can be either stored on spherical coordinate systems like with longitude and latitude, or they can also be northing, easting, x, y flat coordinates with a planar projection and cover other value fields like cadastre topography, land cover, population density, etc. But the core point here is that our world is continuous, and these individual coordinates, they sample a value at one particular location. So on the left, you can see the longitude, latitude of one particular location. If that value there is the reflectance, and you have the reflectance in a particular grid, then you have an image. On the right, we have these vector fields that can describe our world in a more semantic way as zoning or parcels or wetlands or land cover. And those are all useful data and data formats for us. So what is very common here is to discretize our continuous world into vector and raster data. And using this geospatial data in these formats is a very common field in the geoinformation sciences and remote sensing, and there's plenty of established tools and databases available to have this data, convert this data, and process this data efficiently. But then we're still sampling this continuous space over a set of discrete points, and that has some implications to it. For instance, in raster, we need to choose what is the raster size, even though in the real world, we don't have a raster size. So another approach that is a bit more niche is to actually learn a approximation of this underlying continuous function on our geographic world. And while this is definitely more of a domain science niche problem, it's still something that people in the earth sciences have done. So I'm a geodesist by training, so the earth gravity field is close to my heart. And what you can see here on the left is the geoid undulation, so the differences from the earth height in some sense from the reference ellipsoid. And the crucial part here is those data are usually not stored in terms of a raster, but stored as a set of weights for spherical harmonics. And I go into that a bit more in the next slide, but I want to stress that the earth sciences have been working with these approximations of this world as a continuous function also since a while, and I put the reference here of the Gastel book chapter from 2008. So there's an established field in that, even though it's much more niche than storing data in a vector or raster format. So let's go a bit more into detail how spherical harmonics work as an example, also to lead up to the second and third parts. So how can we learn a continuous function over a spherical geometry? And the idea here is to break it down into orthogonal basis functions that are defined on the sphere, and those are spherical harmonics. You can see some spherical harmonics up to degree 3 here on the right, and each of them is orthogonal to each other, and that means that when you add them up with associated coefficients, so have 0.5 for the base harmonic, for no harmonic, and then just an offset, and then minus 0.2 for the first harmonic, etc., and you add them up, you can approximate or can learn a very complex function on the sphere without really having to sample that on discrete points, which is a nice property. But obviously, the more harmonics you have, the higher resolution you have at the end, and the more coarse that image becomes here on the left. And this may sound familiar, this idea of having base functions with coefficients and approximating other signals. And that is because it's basically like the same principle behind Fourier series. Just in Fourier series, the base functions are sine and cosine functions, and you can also approximate an underlying 1D signal with a high number of frequencies with different sine and cosine basis functions. So I think that should feel familiar to everybody working a bit with signal processing. But let's go back to the sphere, because we're talking about geographic data, and look a bit at like this equation, how spherical harmonics work. I mean, it's at its core not particularly complicated. So we have these coefficients, we have the spherical harmonics. If we just look at a single coordinate, then the y at this coordinate just becomes a scalar as well. And then you just multiply this weight with the scalar and the two sums. You could actually just put them into one sum if you just concatenate all of those like triangle harmonics and triangle weights if you flatten that out. And why am I showing this? Mainly to show some similarities with neural networks down the road. So this should already look familiar somewhat, but when we write that out as a vector, a dot product, a matrix multiplication between like some weights and then a vector of features, that is pretty much an affine transformation. And now the step is not very hard to actually put a non-linearity around this. And then we have a single neural network layer, a single dense layer. And then if we stack multiple layers, we have a multi-layer perceptron. So you see it's the same principle. It's all about matrix multiplication. Like anything in deep learning is about matrix multiplications. Yeah? So why am I going this line of showing these similarities? Because for spherical harmonics, it's very natural for us to think about the weights and the harmonics to store data. But usually we use neural networks to rather do prediction or classification. But we can also use neural networks in this other way of actually storing or representing data in the neural network weights. And you see mathematically, it's the same type of idea. You just use a different set of functions or different weights in a different configuration to store that information. And crucially, here the idea or the term that is relevant here is implicit neural representations. Because by training this neural network on a set of data points in a specific way, we learn or represent information from a scene or from the over geographic space in the neural network weights, and that is an implicit neural representation of this data or this information that we encode in the neural network weights. So I hope that makes sense. That mathematically those weights can be used very much to store data. So we are not really bound on this like gridded, discretized format, but similar to spherical harmonics, we can use neural networks to store this type of data. And we're not doing predictions in that sense, where we want to generalize or learn patterns. So implicit neural representations, some people may have heard about them already in like computer vision. So they are really popular and really successful here in the form of neural radiance fields. And the underlying idea is the same one. It's a different domain and a different problem, but we are also storing information about a scene in the weights of a neural network. And the way that works in nerves is that you have one 3D scene with different images from different angles. And these images like basically are samples from this different scene, from this individual scene. And you train this network to reproduce the RGB values on those images, given the coordinates and the direction of individual rays, so individual pixels in that image, essentially. And what is this neural network doing? It is inputting the coordinates, so a position and a direction of this light ray, and it outputs the RGB and the density along this light ray. And the crucial part, after you train it on various images from different scenes, is that the information from this 3D scene is then stored in the weights of this neural network. That's why it's an implicit neural representation. And like anything in like research, you can look at different fields and like to think about still what are the lessons learned from computer vision and other fields in this discipline of implicit or learning information and in neural network weights. And there are basically two things that have come up here that are quite relevant to note, also a bit in preparation for the second and third part of this talk. So the first thing is that positional encoding of coordinates is quite helpful. So here you can see on the right the task of reproducing an image, basically inputting the x and y, so the row column coordinates of a pixel, and then the neural network needs to reproduce the RGB value at this particular coordinate, and then you store this image raster basically in the weights of the neural network. But what turns out is that if you just put the coordinates into a normal MLP, you get a blurry image like here on the top, because the MLP cannot really resolve or store that information very efficiently. But what helps very much is to put a positional encoding on both of the coordinates, and then with sine and cosine basis functions and increasingly high frequencies, and then, as you can see on the image on the bottom right here, you have a very crisp reconstruction of that image, and the neural network is able to learn or store this data much more efficiently. So one lesson learned, positional encoding is important. The other lesson learned that I want to talk about is, let's think about the activation function in the neural network. So classically, if you think about a multi-layer perceptron, you usually think about ReLU activations because they are fairly simple, like putting everything negative to 0. And they're also very effective for classification and regression problems. And in the classification case, the intuition behind that is that you want to extract individual features and you want to set all the irrelevant stuff to 0 and only like highlight or amplify the positive features or the features that are relevant for this classification. And for these types of cases, ReLU is a really good function because you literally implement this setting things to 0 and making not relevant features irrelevant and highlighting or keeping positive features. But when it comes to learning representations, those may not be optimal because in those cases, we don't want to do classification or feature extraction. We want to store a signal, like an image and two-dimensional signal, for instance, in the neural network weights. So what Vincent Sitzman shows really nicely in his paper from 2020 is that if you change the ReLU activation functions to sine activation functions, you have sinusoidal representation networks. So fancy name, but it's actually just changing the activation function to sines. And here, these networks are much more able to learn high frequency, reconstruct images very, very accurately. And not only images, but also 3D scenes, for instance. So on the left, you can see an image, like a video reconstruction of a cat with the ground truth on the top. And you see that the ReLU images are fairly blurry, but the siren reconstruction is fairly good. And we see that as well in the video. Those are basically all the frames together. So quite nice visual to see that sine activation functions are a good choice when you want to store information in the weights of a neural network. So far, excursion from NeurIPS. Let's go back into geospatial domain and do a little bit of a recap. So our world is continuous, and usually the way we store geospatial data is in discrete formats like vector or raster. And there's plenty of tools to really convert between one of the two, like by interpolation or rasterization. And there's a very established field on geoinformation science. But there's the second idea of actually approximating this underlying continuous function with a family of functions like spherical harmonics that allow us to do that as a set of basis functions. Especially in the second field of approximating this underlying geospatial nature, continuous geospatial functions, there's a potential in neural networks, basically, to use neural networks as the new family of very effective universal function approximators to store geospatial information in its weights. And that is essentially a location encoder. It is a neural network that encodes this spatially continuous function from coordinate value samples. And in that case, it's an implicit neural geo-representation. So I hope that was a good overview over how we can use neural networks in a different way, not doing classification or regression, but actually storing data by approximating an underlying function. And in these cases, when we approximate this underlying function, things like positional encoding in the coordinates or sine activation functions make sense, while they don't make sense in a classification case where, for instance, ReLU activation functions are quite useful. But Let's go into detail now in the second part here on location encoders. So how can we actually implement these neural networks for geospatial data that store this geospatial information? So this will be one line of research that will be leading up to the third part. And I want to talk about two types of data. The first one is I like to illustrate this problem. So the first one is a toy example of land-ocean classification. So we define a function on the sphere based on if it's on land, then it's like a 0. If it's on water, it's 1. And we can sample from this function training, validation, and test points. So train validation points in a randomly distributed, and test points in a regular grid, as you can see here on the right. And it's also evenly distributed on the globe. It doesn't look like this on this map, but the Earth is a sphere, so that's how it's still evenly spread out. And the objective is to use these samples from this underlying function and to reconstruct this use the samples of land and ocean across this geographic space and then reconstruct this underlying function as good as possible. And the other application I want to talk about is species distribution mapping, which has been driving this field quite a bit. So one big benchmark data set that is used here a lot is iNaturalist, which is a quite challenging image classification task normally, but it has 430,000 georeferenced images and a very high number of individual species, so 8,000 different categories, which is quite a challenging problem. And the core situation here is that different species, like here the Arctic fox, may look very different in the summer with a bat-eared fox. But if you know the coordinates, you may actually have a higher accuracy, or it may help the classification of those images if you also bring in the coordinate information. So in terms of coordinates, you really want to learn a distribution map. Given this coordinate, how likely is this species to be present? And that's how we will use basically this data set, mainly for the location encoding, that we want to learn a map from individual points or observations that gives us a probability how likely this species will be found at this individual coordinate. So the classic approach here to do this is to do interpolation. So we can use this classic geostatistics, geoinformation science tools, where we use the training data, so the individual observations of the species, in the other data set, the land-ocean points, and then we can interpolate between individual support or training points, and then get a probability if the species is at that location, if the species has been observed in the vicinity. And it's a very established problem, but there are some issues with it. So it's a non-parametric approach. So we need to store the training data somewhere, and then we need to calculate similarities of a test point to the training data. Basically, we do this with kernels and Gaussian processes, or by defining a similar distance metric with the interpolation techniques, or variogram and kriging. And these lookup of where is the corresponding training points that are closest to a test point, that is a fairly computationally expensive problem when you have a lot of points. So classically in kernel-gram matrices, you have to calculate a lot of large kernel-gram matrix. And here is a potential in neural networks as well to learn these relationships by implicitly encoding this training location data in a neural network. So the idea is you have these species observations or land-ocean classification observations in X and Y. So they have the coordinates and the value that is predicted, and then you have the ground truth of what is actually this value that is in your data set, and then you can do normal stochastic gradient descent and adjust the weights, and basically to learn this implicit neural representation of this training data. And the core idea here is that you do this training once, you encode your training points in your neural network weights, and then you don't have to look up the original training points anymore. You just have to do forward inference through this trained network, because the original training point locations have been already encoded in the weights of this neural network. And after being trained, it's computationally linear, and training is linear, and which makes it much faster if you have a lot of points. And it's a kind of emerging field to test this, and it's very compatible. That's the other benefit with integrating these models then into other deep learning networks where you input the coordinates through a location encoder and then put out a vector and put that into an image classifier, for instance. And let me give you one example here from a recent ICML paper from Elijah Cole, who use neural networks exactly for this purpose. So they have been doing a lot of work together with Oisin McKay, especially on species distribution mapping with implicit neural representations. And here's the same principle again. So you have your input data, so individual training points from the species, of species green, blue, and red. You train this neural network, the species range model, they call it, and then they predict the probability. They try to reconstruct the training data basically during training time. And what you see here on the bottom right, where you see the species range, is that there is an inherent smoothness to neural networks, that if you then at test time put in a coordinate that is not exactly on one of those training points, but somewhere in between or somewhere in the vicinity of a training point, the neural network will still predict the probability for the species in the vicinity of the training data. So that's the lightly more transparent shaded areas are indicating this. So in that sense, we're really doing an interpolation between the training points without really having to look up what are the individual training points, because these training points are already encoded in the weights of this neural network. And the nice thing here is because they know what they're doing and they do some analysis of the model that is trained. And if you then look at the penultimate layer, before the decision layer, so they call it the encoder, and you do a PCA on these types of features, you see that the features that are encoded around the globe follow geographic patterns. So that makes complete sense, because some species are living in like mountains, others in the forests, and the neural network here, the species range model, has to learn these types of patterns, geographic patterns, to do the classification of which species are present. So that is a nice example of why these location encoding models, how they are operating in terms of interpolation, which is a slightly different angle to think about location encoders. So how can we implement this species range model or this neural network or this location encoder network? So at its core, it's inputting geographic coordinates and it's outputting a scalar or a vector corresponding to this geographic coordinate. And from the lessons learned in part 1, I think it's clear that a positional embedding is helpful. So there's no trainable weights here. And then you just spread out the coordinates, longitude, latitude, into a higher dimensional vector of preferably multiple frequencies. And then you put that through a neural network to store and mingle that with the weights and the information that is learned from the training data. And there's been a nice review from Genshin Mai on this, where he summarized the whole series, also a lot of his work and related work on a review on location encoding in GeoAI, which summarizes this very nicely. And here has been a lot of work in how to design this positional embedding. Yeah, that's on the left side. So there's been a series of positional embeddings proposed in the literature. I go over some of them in the next slides. But the neural network has not seen a lot of interest, like up to recently. So what is very common is that Oisin McKay has started this research line more or less with this GeoPrior paper. And most of the follow-up works use this FCNet that was proposed by him primarily, with basically is a ReLU network with some skip connections, and that works reasonably well. And most of the follow-up works proposing grids, sphere C, etc., were basically using this neural network as is. But let's stay on the positional embedding and follow this research line of different positional embeddings. So in one initial paper from Oisin McKay, he addressed one problem basically. It was kind of an heuristic idea here that if you put in the coordinates longitude and latitude directly to a neural network, you get a problem at the date line, because the longitude jumps from minus 180 to plus 180. And that is a discontinuity that you really don't want, right? The world has no discontinuity at minus 180 degrees. It's just a sphere. So the easy fix to address this is to use sine and cosine functions around longitude and latitude, and then you basically wrap the world around a cylinder, and that helps with the state line discontinuity. But you can follow up this work, like here with work from Genshin Mai, of actually making these sine and cosine positional embeddings with multiple frequencies. And he shows quite well quantitatively at large scale that using more and more higher dimensional vector from this positional embedding with higher and higher frequencies is quite good for the reconstruction. And this should look really familiar if you listen to the first part, because it's basically like Fourier series are working again, and in the same lesson learned from implicit neural representation. So what is happening here is that experimentally, in that case, we see that higher and higher frequency sine cosine basis functions really help with encoding, with the performance of reconstructing this geographic data. And it has been summarized as well in this review paper, is that all of those positional embedding functions, they are subforms of double Fourier series. So double Fourier series are the idea of using longitude and latitude and doing a Fourier transformation, a Fourier series on both of them. And that yields basically this very long equation that has any possible combination of longitude and latitude at any possible frequency, up to a maximum frequency, and this is called S in this case. But the core point here, those are all sine and cosine basis functions, which makes this a Fourier series. And in fact, all of those positional embeddings proposed in the last years can be seen as a subpart of these double Fourier series. So the double Fourier series are basically all of the gray points that represent longitude and latitude at various frequencies. And you can see that rep, for instance, is only the sine and cosine, only the frequencies at the base frequencies, while the grid basically has higher and higher frequencies involved as well. So what I want to say with this, that all positional embeddings, they are basically based on the double Fourier series subset. And that leads a bit to a knowledge gap or a research gap that we identified, and that leads up to our third part, is that this Fourier series composition does not really reflect the geometry of our world, because we are living in a sphere and not a map. And this double Fourier decomposition assumes a rectangular domain between longitude and latitude. And that leads to some artifacts, as you can see here on the right, where at the poles, when we try to do land-ocean classification, we get some discontinuity. And the second research gap that we saw is that the FCNet that was proposed by Oda, that was basically reused without really considering the latest or the new knowledge we have from implicit neural representations in other fields. And what about serial networks, right? What about when we change this ReLU activation function to a sine activation function? And this basically leads me to the third part, which basically joins the foundations in part one, like what we learned of implicit neural representations in machine learning and what we know about spherical harmonics in the earth sciences, together with the location encoders, mainly on the species distribution mapping, to summarize a bit on one of our recent papers that I'm happy to talk about. So our proposition here is, let's use a location encoding network with spherical harmonic basis functions and sinusoidal representation networks. So that's basically the paper in one slide. And the core idea, and I think given the context before, it should be somewhat intuitive, is that we should use basis functions that are not used based on sine and cosine functions, but spherical functions like spherical harmonics. And then together with a really simple neural network, which is literally a small MLP just with sine activation functions. And I would like to stress again here that when we leave away the siren for the moment and we just focus on this linear neural network, we're doing nothing else as we would do in the earth sciences since 2008. So when we see this weights that we multiply with the spherical harmonic basis functions, like in a linear way, if we see that as a linear layer, we can see that basically as a location encoder with spherical harmonics as a position embedding in a linear layer as a neural network. And you can see that on the right as a visualization. And when we train, basically when we fit this weights with stochastic gradient descent, like we pose 0, 100, and 450, so after training, we see that even with just a linear layer, because we have these spherical harmonic basis functions, we can reproduce this underlying function relatively well. So, and I want to stress here that we are not doing anything particularly different from the earth sciences before. But what if we bring in this, we just put it in a different framework, in this location encoding framework, where we think about things in a positional embedding in a neural network way. So what about we add now Siren to this, and we replace this linear layer with a proper neural network with multiple layers. And what we see is that we can then suddenly approximate a much more complex function without needing a lot of spherical harmonics. And that is basically our proposition here, that we should use spherical harmonics with the Siren network so that we can approximate really well functions on the entire globe. And what we see is that the number of harmonics are a parameter here. So more harmonics means we can resolve a higher frequency. So here we see the example with a linear layer, as we would do in the earth sciences. But with Siren, we can get an even higher resolution, because this neural network that has multiple layers and the nonlinearities can superimpose multiple frequencies on top of each other, and when you get a fairly crisp reconstruction of land-ocean maps. So to close up a bit with like some quantitative results, to show a bit of a kind of experimental setup on the land-ocean classification and the iNaturalist benefit of location over image classification. So positive number means location has improved the classification of images. We see that this naive approach of putting coordinates without any positional embedding into a ReLU network like FCNet is not performing particularly well. So I think many of you may have thought about putting coordinates into a network and just put them in as a new feature, and then like it was fine, but it could have been better if you would have put them through a positional embedding with a ReLU network. So here we show that that is not optimal, and it's better in that case for a ReLU network to put in a positional embedding function before. But what we also see that with the right set of basis functions for the sphere, like spherical harmonics, the choice of the neural network doesn't matter so much anymore. So even this linear layer that you see here in the second column is performing relatively well, even though it's just a linear combination of weights with spherical harmonics. And the FCNet performs well, and also the SIRENet performs well. And the other finding here is that Siren also works really well, no matter the positional embedding. And we have some explanation that Sirens can learn something that is really similar or equivalent to a positional embedding because of those sign activation functions in the paper. But I'll leave that out for now. So one of the main findings here is Siren works also quite well without the positional embedding. So if you really want to put coordinates directly into a neural network, use sign activation functions, then it will also work well. Or use positional embedding and use some ReLU functions. So here recommendation is right there. But saying that, there's still discontinuities on the poles, because in that case we are still having sine and cosine basis functions. The second part is use spherical harmonics for the global scale. Coordinates at higher altitudes, or the accuracy at higher altitudes matter. So we have a toy example here on predicting a grid, and we show fairly clearly that the sine and cosine positional embeddings like sphere plus and grid are losing in accuracy a lot if you go to higher latitudes. But if you use the right basis functions for the sphere, like spherical harmonics, you keep a high accuracy. So here you see some artifacts on the top right, and when I have some nice animation around here, but if I change to the spherical harmonics, you see that the artifacts are gone. So far to this paper, some conclusions and some concrete recommendations. Here, Sirens are a good neural network for any location encoding problem, and spherical harmonics are good for global problems where the spherical geometry matters. So if you take something from this part, then like Sirens are good for location encoding, and spherical harmonics when you want to go to high latitudes and the poles, or you would like to look at the entire globe. So some overall takeaways to wrap up this talk, and I hope you have enjoyed it so far. So in the first part, I covered some basics and foundations, where we usually discretize our continuous world through vector and raster data. And there's well-established tools around this. But we can also use deep neural networks or deep location encoders to approximate these continuous functions with as an implicit neural representation with neural networks. And the lessons learned here from NeurIPS is that positional encoding is helpful and sign activations are helpful. So that is something to keep in mind for these implicit neural representation problems, or where you want to store data in neural network weights. In the second part, I talked about location encoders and this research line that has somewhat independently emerged, mainly motivated by species distribution mapping. So the idea here is that you have a location encoder also with positional embedding and a neural network. And you have this non-parametric positional embedding to put the coordinates into a higher dimensional vector of higher frequencies, usually in that case not too different to a Fourier series. And then you use the neural network with weights to store the geospatial information. And these can be trained basically with gradient descent by reconstructing values at any points, which is nice because you can implement everything in Torch and it works. And the third part on an location encoding paper where we analyze both of those lines in depth is that with the siren, with sign activation functions, we would recommend that clearly for any location encoding problem over like a ReLU network. And spherical harmonics are a good choice for geographic data at global scale where the spherical geometry matters. And with that, I hope you have enjoyed this talk. It was a pleasure to present the basics around location encoding to you. You're in very competent hands with Konstantin, and I'm looking forward to meeting you at some point in the future. Have a good rest of the workshop. Goodbye.